In the previous example, we have successfully employed differentiation of power series to compute representations of new functions in terms of power series. In example 5, we will use integration of power series to obtain power series representation for an important function. So, example 5, let us find the power series for the function log of 1 plus x and determine its radius of convergence. So this example doesn't make it explicit at which point our power series should be centered. So we will employ power series centered at 0. So how do we start about producing such a power series expansion? Well, we have to relate log of 1 plus x to other functions that we already have representations for. So first observe that if we let f of x be log of 1 plus x, then the derivative of f of x is 1 over 1 plus x. And this here can be easily represented by power series. Indeed, we have 1 over 1 plus x is equal to 1 minus x. Right? And since we have seen previously how to represent 1 over 1 minus x in terms of power series, it is equal to the sum of the geometric series like so. It's the sum x to the power k, and in this case our x is replaced by minus x. So this is the power series representation of 1 over 1 plus x. We can further simplify it by taking the minus 1 outside of this factor, outside of this term. So this here becomes the sum k from 0 to infinity, minus 1 to the power k times x to the power k. Now, when is this convergent? This is a geometric series. It is therefore convergent when the absolute value of r is less than 1, or equivalently, because minus 1 does not change magnitude of a number, this is the same as to say when absolute value x is less than 1. So here we have power series representation for f prime of x, and we know it is convergent when absolute value x is less than 1. So once again, the equality we have just obtained looks like this. F prime of x is equal to minus 1 to the k times x to the k when absolute value x is less than 1. Since our goal is to represent f itself in terms of power series, we will take this relation and integrate both sides. So let us integrate both sides. So we know that we can integrate power series, and integration preserves the radius of convergence. So if we integrate both sides, on the left we will have f of x. So that is integral of 1 over 1 plus x. So So that's log of 1 plus x. That's precisely the function that we are looking to represent by power series. And on the right-hand side, we will have the integral of the series. K from 0 to infinity. We know that power series can be integrated term by term. So this is simply the sum k from 0 to infinity integrals of these expressions. Okay, so now basically our goal is to compute the antiderivative of this guy here. Observe that minus 1 to the k is just a constant. It's independent of x, so we can write this sum like so. And the integral of x to the k dx is simple, right? This is simply integral of a power function. So we end up with the following series. And we will add a single integration constant for all the antiderivatives. So what we are saying here is basically we are choosing the antiderivatives in each integral like so, and then we have a single overall constant of integration over here. This can be further simplified by changing indexing. So first let us conclude by saying that this is the power series representation for f of x. We know that it is convergent for absolute value x less than 1. Right? So this is because integration preserves the radius of convergence. And of course, we are not saying anything about the endpoints. The endpoints of this interval, x equals plus minus 1, need to be checked separately. So what we are saying here is precisely that the result of integrating this series term by term converges for absolute value x less than 1. We are not saying anything about the endpoints. It may very well diverge or converge. We don't know what it does at the endpoints. Now, as I mentioned, we can further rewrite this series in a more convenient form by changing indexing. So observe that here we're starting at k equals 0. So the lowest power we have in our series is 0 plus 1, so that would be x to the first. So we can represent f of x, which is the log of 1 plus x, by the following series. So let L be k plus 1. Then this power series here becomes sum from L equals 1 to infinity, right? Because when k is 0, here L is equal to 1. And then we have minus 1 to the power, say, L plus 1 times x to the L divided by L. And then plus a constant. So we wrote here L plus 1, even though we have k in the original power series, right? That is because minus 1 to the k is equal to minus 1 to the L minus 1, right? Because k is equal to L minus 1. So we have k is L minus 1, but minus 1 to the power L minus 1 is equal to minus 1 to the power L plus 1, because the difference between these two exponents is 2. So we have minus 1 to L minus 1 times minus 1 squared. So these two numbers are equal. And we have this power series representation. Now we are not done, even though we have successfully obtained a power series representation. We're not done because we have to determine the constant of integration, right? So let us now determine C. So let me rewrite again this expression for f of x we have. Now using k once more time for the index in the infinite sum. So this is the representation for log 1 plus x we have, plus c. And the question is, what is c? To determine c, we will substitute x equals 0 in here. Okay, what does this result in? Well, when x is equal to 0, on the left we have log of 1 plus 0. So that is log of 1, which is 0. And on the right hand side, we have the sum k from 1 to infinity, minus 1 to the k plus 1 times 0 to the k over k. And this entire series is simply 0. And so we have 0 equals 0 plus c, which gives that c itself must also be 0. And so the conclusion is that log of 1 plus x is equal to the sum k from 0 to infinity minus 1 to the k plus 1 x to the power k over k. And so this formula will be useful in what follows, and this is something we will want to remember. So let us summarize what we have done here. Using integration of power series, we have obtained this formula for the log of 1 plus x. The formula holds when absolute value x is less than 1, and we have, as we have said previously. And so this will be a rather useful expression. We will use it in many subsequent occasions. So let us now proceed to obtain a power series expression for another important function. So in the example 6, we will obtain the power series expansion for f of x equal to inverse tangent of x. Okay, so the plan we will follow here is similar to what we did in the previous example. We will start by computing the f prime of x in the hope that f prime of x is a simple function and we can obtain its power series expansion using what we already know, and then we can just integrate term by term by using the theorem that we have for power series integration, and that will give us the power series representation of the arctangent itself. So f prime of x is 1 over 1 plus x squared. Now the question is, can we represent this function as a power series? Well, this will again be reduced to the geometric series representation that we have by saying it is equal to 1 over 1 minus x squared. And so you see that this is again of the form 1 over 1 minus x, which we can represent by power series. So it's just the sum of the geometric series, k from 0 to infinity, x raised to the k, except that now the role of x is fulfilled by minus x squared. And let us now simplify this expression. So this power here becomes minus 1 to the k times x to the 2k, k from 0 to infinity. Great. So this gives us the expression for f prime of x as a power series. When does this power series converge? Well, it converges by being a geometric series. It converges, or maybe I should say we're looking at this series here. So this is a geometric series with minus x squared as the r, so it must therefore converge when absolute value of minus x squared is less than 1, and precisely for such x's. And so this is the same as to say that absolute value x squared is less than 1. And then by taking square root of both sides, we conclude that we must have that absolute value x less than 1. And so this is precisely when the power series for f prime of x converges. So let us integrate both sides of f prime of x equals sum k from 0 to infinity minus 1 to the k times x to the 2k. Right? So this equality we know holds when absolute value x is less than 1. So by integrating both sides, on the left we get f of x. So f of x, which is, remember, arctangent x, is equal to the integral of this power series by the theorem we have for integration of power series, this integral is simply the sum of integrals of individual terms. So this factor of minus 1 to the k is a constant. And I have minus 1 to the k times the integral of x to the 2k dx. And again, as it was in the previous example, all I need to do is to integrate this power function, which is quite straightforward. I'll have the sum from 0 to infinity, minus 1 to the k, times, this being a power function, I increment the exponent by 1 and divide by the new exponent. And then I will add the constant of integration, just as I did in the previous example. Great. So this is the power series representation for inverse tangent of x. It converges for absolute value x less than 1, because integration preserves the radius of convergence, right? And we started with the power series centered at 0. This power series here is centered at 0, and it has radius of convergence 1, obviously, from this inequality. So then, once we have integrated it, we again have a power series centered at 0 with the radius of convergence equal to 1. So this exact interval convergence. Again, we are not saying anything about the endpoints. So this series may still converge at the endpoints. So let us make a remark. We are not saying anything about the endpoints of the convergence interval. And these are, of course, x equals plus minus 1. So these are the endpoints of the interval absolute value x less than 1. Now it remains to determine what C is. We have computed power series representation. We know when it converges. It remains to determine what the constant of integration is. So to determine C, again, what we will do is set x equal to 0. So that will make this entire series vanish, and we will be able to compute C. So set x equals 0. Then our equality becomes f of 0, which is arctangent of 0, is equal to the sum k from 0 to infinity minus 1 to the k 0 to the power 2k plus 1 over 2k plus 1 plus c. So of course this entire series is 0 because every term with positive exponent, and they all will have a positive exponents, as you can see, because indexing starts at k equals 0. So the powers start at 1. So all these terms will be equal to 0. The entire series consists of such terms, so the entire series is 0 as well. And finally, inverse tangent of 0 is 0 again. And we conclude that 0 is equal to 0 plus c. So c must also be 0. And now this gives us the second important formula from this video. Arctangent of x is equal to the sum k from 0 to infinity minus 1 to the k x to the 2k plus 1 over 2k plus 1. And so this holds for absolute value x less than 1. And so this is the second important formula we obtained in this video. We will often make use of this formula for inverse tangent as well.